Hi everyone. This video is about the point-slope form of a line equation. A big part of this course is understanding and manipulating different representations of the same relationship between variables and constants. We did this when we solved equations and inequalities, and we'll continue with our exploration of lines. It's helpful to remember that a line is the visualization of a solution set to a linear equation. Every point on a line is an ordered pair that we've been referring to as some x sub n, y sub n. And these x and y values in an ordered pair make the equality that is the line equation a true statement. So, for example, we have the case using our slope-intercept form of y is equal to mx plus b. If we take y is equal to 3x plus 2, we use the subscripts n with x and y to indicate a particular value that we're going to plug into x that generates a y. A specific value of x that creates another specific value of y is the ordered pair. In general terms, we use x, y to represent any value on the line. Let's recall our facts about lines. Any 2 points on a line can be used to create the equation for that line. The slope of a line in any 1 point on that line can be used to create the equation for that line. Equations for lines can be written in different forms and can be algebraically manipulated to change between forms without altering the solution set of the equation. We're going to add another fact about lines. The slope of a line is constant. Let's talk about that last new line fact. The slope of a line is constant. This means the slope never changes. It doesn't matter where we choose to evaluate the slope of the line, it will always be the same. If we choose 2 different places on a line to evaluate the slope, those 2 slopes will be equal. When we look at modeling real-life processes and problems, we'll see how useful that fact is. Take a look at an example. We'll use the equation that we just had up here to generate some points from our slope-intercept form. And let's pick some values. So we're going to choose point P0, and we'll pick an x value of 1. When we plug 1 into this, we generate a y value of 5. Let's pick a second point, P1, and we'll just choose an x value, 2, and when I plug 2 into this, I get 6 plus 2 is equal to 8. We'll choose a third point, P2, and for this one I'm going to pick an x value of 5. And when I plug 5 into my x equation, into x in my equation, I get 3 times 5 is 15 plus 2 is 17. And we're going to pick one last point. And for this one, I'll choose an x value of 9. And when I plug that in, I get 9 times 3 is 27, plus 2 is 29. These are all ordered pairs that make this equation true. Let's take a look at calculating the slope for each of these in different combinations. So we'll choose P1, P0 and P1 is our first point. So let's calculate M. We know that M will be equal to y1 minus y0 divided by x1 minus x0. And let's plug those 2 values in. those 2 points in. So we have, remember that when we write these are our y coordinates on this side, and this is our x coordinate that falls down this line here. So if we take our y1, this is going to be 8, minus y0 is going to be 5, and then we put that over x1, which is going to be 2, minus x0, which is 1. This is equal to 3 over 1 is equal to 3. Let's take a look at points P2 and P3. And we're going to calculate the slope for those two values also. And try to get out of the way here so you can see that. This is going to be y3 minus y2 divided by x3 minus x2. Notice the subscripts always agree. We had x1 and y1, we have x0 and y0, we have x3 and y3, and x2 and y2. This is important. So we're just going to plug the values in here. We have 29 minus 17 divided by 9 minus 5, and this becomes 12 divided by 4 is equal to 3. So both of these pairs of points that were generated from this line equation create the same slope. With this type of measurement, this is what we should get. And in fact, this agrees with the slope that we have in our initial equation that we generated these points from. So we can actually, let's go one step further, and we're going to use P0 and P2 to create slope also. So we'll do y2 minus y0 divided by x2 minus x0. And now we have 17 minus 5 divided by 5 minus 1, and this is equal to 12 divided by 4 is equal to 3. Once again, it all agrees. It doesn't matter which 2 points we pick on our line. When we use our slope formula, we wind up getting the slope of the line. It doesn't matter where we pick those points. We're going to use this idea to reevaluate our slope-intercept form and change that into something a little bit different. We can look at a graph of our example equation that includes the points from our example. All those points sit on the line. We had 1, 5, 2, 8, 5, 17, and 9, 29. The line is a graph of y is equal to 3x plus 2, which was our linear equation. The slope that we calculated for each of those was always 3. Notice on line 2 that the slope is 3. We looked at just a few points. In this particular case, I've added a general pair that can move over the entire line. And we'll start all the way back here. Now, look at M as this point moves over the course of the line. This is the slope that's being measured from the difference between the y coordinate of our movable point and our x coordinate of our movable point. We're subtracting our initial point, the x and y, from the x and y of the movable point. And as this point slides up along the line, the slope never changes. Since it doesn't matter where we pick the second point, we'll leave off the subscripts for that second point, and we'll write the second point as a general ordered pair that is part of the solution set. And as we said, we just denote that as some point x, y. It could be any point at all. So when we consider, we used to have m is equal to, say, y2 minus y0 and divided by x2 minus x0. We're going to take this idea of a general point and we're going to replace our y2 and our x2 with this general point. And we are going to write this as m is equal to y minus y0 divided by x minus x0. We know from solving equations that we can manipulate this relationship algebraically, and we can produce a general equation that represents any change in y relative to y0 from any change in x relative to x0. So if we take a look at this, let's get rid of this portion here. I'm going to choose to multiply both sides by x minus x0, and I'm going to put parentheses around that. And I have to multiply the same thing on this side. And on the right side of this equation, the x minus x0 cancels, and what I'm left with is m times x minus x0 is equal to y minus y0. And I'm going to try to slide out of the way here so you can see that. And I'm going to rewrite this over here in just changing sides. And what we have is y minus y0 is equal to m times x minus x0. Where x and y, or x and y without subscripts, are the general variables that we have, and x0 and y0 represent a specific point on the line. This is the point-slope form of a line equation. Let's take a look at our point-slope form of our line equation, and we're going to manipulate this a little bit to see how this relates to the slope-intercept form of a line equation. So the slope-intercept form is based on the idea that there is a single point that we're concerned with, and it's the y-intercept. But the y-intercept is always some point 0, b. It occurs at x equals 0, and we call it b. So why don't we take this and plug this particular point into our general equation. So we have y minus b is equal to m times x minus 0, but x minus 0 is the same thing as x, so we are just going to rewrite this as y minus b is equal to mx. We're going to use our equation solving techniques to get y by itself. We're going to add b to both sides. And what we're left with is y is equal to mx plus b, which is our slope-intercept form of our line equation. Let's darken that up a little bit. Time for a new pen. We can generate the point-slope form of the equation by plugging in any ordered pair that sits on that line. And notice that while the representation changes in these examples, the solution set, which is the line, doesn't change. So this red line represents y is equal to 3x plus 2. If we use the point-slope form of our equation, using each one of these individual points, this first line here uses point x equals 1, y equals 5. The line is the same. The color just changes here to indicate that this is the line that's being shown. We can look at the point 2 and 8. Again, the solution set doesn't change. Its representation does change. We can look at the point 5, 17, and once again, the line remains the same. The solution set remains the same. The representation changes. And finally, for our last example, we have the point 929. And we're just plugging those values in to our point slope form. And once again, the solution set is the same. As an example, let's write the point slope form of a line with slope equal 5 that passes through point 6, 17. Well, we have our y minus y0 is equal to m times x minus x0. And all we're going to do is take our slope value and our point and plug those values in. So y minus y0 is going to be 17, is equal to m, but m is equal to 5, times x minus x0, but x0 is 6. And that is the point slope form of a line with slope 5 that passes through point 617. Take a look at the next video that demonstrates how different types of problems are worked to produce the point slope form of a line. Thanks.